Hey everyone, as most of you may know, my name is Pamelo and I am your TA for EEE2041, Intro into Electrical Engineering and Power Utilization. So today I'm just going to be walking you through some of the basics that you're going to need to know when conducting some of our labs, like how to use your oscilloscope, signal function generator, and power supply. And I'm also going to be walking you through the use of a breadboard.
Starting off with the function generator.
Now, for this machine, how you would typically turn it on is by pressing the leftmost button, which is the power button, to switch it on. Now, you might need to wait a few minutes, or rather a few seconds for it to just power up properly. Okay, there it is. Now, for this machine, we have a wide range of signals that we can select, which include our sine wave, square wave, ramp wave, pulse wave, and maybe also like a noise wave, but you guys don't have to worry about that for now. Now, we're just going to start off by using our sine generator. We're pressing the sine button, and we'll first look at how to set the frequency. Now, that should be the first thing that pops up on the screen. As you can see here, this is the frequency. It's in kilohertz already. How you would typically adjust this is by pressing the numbers. Let's say we want 50 kilohertz signal, which is the typical South African frequency. You just go back here and press 50, and it's in hertz. You can select your scale using those blue buttons there. We want 50 hertz, and there it is. Now, to move on to our amplitude, or rather the voltage, you just simply press the second button, which says amplitude, and here we have a chance to select our peak-to-peak voltage. Now, let's say we want a 2 volts peak-to-peak. We simply just put in 2, and then we go to the bottom buttons to select our scale as well. We'll go here, 2 volts peak-to-peak. Cool. And now moving on to the offset button. Now, typically we don't really require this, but if you wanted extra information, how you go about setting that is literally pressing that third blue button, and you'd adjust your value there, which would move your signal up or down by that certain amount you put in. But for this purpose, we require 0 peak-to-peak voltage, and that will be in DC. And yes, we're done. Now, one important fact that you should know is if your signal is not displaying on your oscilloscope, you need to press this output button for it to show up. So please remember this output button. It is a very common mistake that people make, and when they ask tutors what's wrong, it's literally just pressing a button. But yeah, that's how we would use our function generator. Now, moving on to our oscilloscope. For this machine, we typically use a BNC connect and your scope probes. Now, this has 2 different terminals which you can hook up to the positive and negative terminal of your circuit. Now, if we can look at our machine, how you turn it on is simply pressing this button and wait for the fireworks to show up. Now, this machine typically takes a bit of a while to warm up before you can start seeing the signal. But I guess for now we can just start off by connecting our probe to our oscilloscope. Now, for this purpose, we're going to be using one channel. Now, keep in mind the oscilloscope does have 2 separate channels which you can use to view 2 different waveforms. Now, this is very useful when you're trying to compare 2 circuits, waveforms, and how they behave. Okay. Now it's clipped in. Now, in order to use our oscilloscope, we actually need to use a signal coming from our function generator, which we set up earlier. Now, you typically connect your black wire, or rather black output, to your other black output, negative terminal, and then your positive to your positive scope probe. Okay, now if you look on the screen right now, we can typically see a rather resemblance of a wave. Now, unfortunately, this has not been scaled properly. How to put this into view? One of the quickest methods is simply by pressing auto scale. Now, this brings your signal into perspective, which you can use to view the whole wave. Now, there are quite a lot of buttons, or rather knobs, which you can adjust, which might be confusing at first, but the main 3 buttons you should remember are the horizontal scale divide, which either expands or contracts your wave horizontally, your vertical time per division knob, which also moves your signal, or rather expands it vertically, and then, like I mentioned, 3, your push to scale, which typically would do the job for you, so you don't need to play around with your horizontal or your vertical scale. Okay. Now for the last part, we're going to be looking at the power supply. Now typically for this machine we use crocodile clips. Now this makes it a lot easier for us to set it up, or rather connect it to our circuit, which is typically on a breadboard. Now if we look at the power supply, it is a fairly intuitive machine. How we would power it on is just simply pressing that power button right there, and we'd be connecting up our terminals into the positive channel and negative channel of the power supply. Now red goes onto the positive and the black one goes into the negative terminal. Now for this demonstration we're just going to be looking at channel 1, but these 2 channels are quite similar, so if you understand one you'll understand the other one. Cool. Now how you would typically set up your voltages and currents is by adjusting the top knob for your voltage and the bottom knob for your currents. Now if you would like to see your voltage on the oscilloscope, you typically have to press the on button to be able to view it.
Now, moving on to breadboards. Now, the figure on my screen shows a typical diagram of a standard breadboard. This, however, might seem slightly different from the one you received from your EEE packs. However, the operation is quite similar. Now, a standard breadboard is typically divided into 4 separate sections. I have labeled them here as sections 1, 2, 3, and 4. Keep in mind, section 1 and 4, 2 and 3 are similar in operation, however, they are isolated from each other. Now, starting off with section 1, you must note that the first row in this section is connected together in series. Now, as I've drawn with the blue line here, this is the connection that goes underneath the breadboard, meaning that all these terminal lines are connected together in series. However, these are completely isolated from the second row of terminals, which is represented by the plus sign. Now, we typically use these 2 rows as our positive and negative voltage sources, or our incoming voltage and ground. Now, moving on to the second section, these ones are connected slightly different from section 1 in regards that the lines, or rather the terminals, are connected. The terminals that are connected in series are vertical instead of horizontal. The horizontal terminals are completely isolated from each other, meaning that there is no connection underneath, as you can see from my drawings. However, as I mentioned before, sections 2 and 3 are completely isolated from each other, meaning that in the middle of these 2 sections there is a break. Therefore, there is no connection. And section 4 basically operates the same as section 1 with regards to the horizontal lines being connected in series. Now, keep in mind with your breadboard, given that it is a tad bit longer, it does have a slight break in the middle of the board, meaning that there is a slight disconnect between the first half of rows and the second half of rows. Now, this is only applicable for the first section and the fourth section. Now, I'm sure you guys are wondering how you typically connect, or rather go about connecting a standard circuit diagram to your breadboard. Now, as you can see from this figure that is now on my screen, I have labeled the terminals, or rather the nodes, of this circuit diagram as A, B, C. Now, these are where our components are joining with either a voltage source or another component. Now, how you position these components on a breadboard is shown in the figure above, where we have a resistor, an LED, and typically our ground and our power supply. Now, node A is connected to our power supply, which I mentioned is the top railing of section 1, and that is connected to our resistor, and then our resistor is taken from that to our row 16. Now, as I mentioned, these middle rows are typically connected in series horizontally, or rather this time the board is switched, so vertically, which means that this is in series. As we can see from our diagram here, we have our node B, and here also our node B. Now, I also mentioned that there is a break in the middle of the board where sections 2 and sections 3 are isolated from each other. Therefore, this allows us to connect our LED across the board, ensuring that current flows through the LED instead of short-circuiting it underneath. And now our current, or rather wire, is going to go from our LED to the node C, which is going to be our series line that is indicated by this blue one here. And this is connected to our ground, or the ground supply, which is connected in series vertically. Now please note that if you were to connect your LED, or rather the left side of your LED on, or rather let me change colors. Okay, if you would have connected your LED to this terminal, it would have short-circuited your board, meaning that you would have created a loop of zero resistance, which means that current would not have flown through your LED if this wire was connected here, and then you would have taken this to your negative railing. And that's how a typical circuit is connected on a breadboard. Thank you so much for listening, and I look forward to seeing everyone in the labs.